Analytical Chemistry 1, Lesson 28. Acids and bases are some of the most fundamental and ubiquitous molecules in chemistry. Occasionally they are front and center in some chemical process, but most commonly they are part of, but a very important part of, the background of most every other chemical reaction environment. Understanding how they behave is an essential part of chemical analysis, molecular synthesis, and all biochemical processes. We need to look at strong acids, strong bases, weak monoprotic acids, weak monoprotic bases, and weak polyprotic acids and bases. When we were investigating the systematic approach to solving equilibrium problems, we used lots of acid-base examples. Now we will revisit these again, but with a focus on their acid-base behavior and applications. One additional point. We speak of acids and bases together because they always occur together. When the molecule has its acidic proton attached, we say it's in its acidic form. When the proton has been removed, it is in its basic form. The two forms are said to be conjugate to each other. The acetate ion is, for example, the conjugate base of acetic acid. And we also say that acetic acid is conjugate to the acetate ion. Every acid-base reaction involves a conjugate acid-base pair. Let's look again at strong acids. There are 6 strong acids you should memorize, and you probably already know them: HCl, HBr, HI, H2SO4, HClO4, and HL3. In dilute aqueous solutions, these acids completely dissociate into an aqueous proton and their conjugate base ion. There are many other strong acids, mainly organic acids such as triflic acid or tocilic acid, and you may encounter them. But these 6 inorganic acids are the most important ones for our class. Because they fully dissociate in water, we are not able to experimentally measure their dissociation constant. It's just really big. There are theoretical methods to calculate them and some indirect chemical approaches. We can give them values for their Ka, but there is a lot of uncertainty, and the details of the chemical environment can change things around. Here are some reasonable estimates for these acids. You can see that nitric is the smallest of them all, but it still fully dissociates in water. The strongest acid known by some measures is fluoroantimonic acid with a Ka of about 10 to the 28. So focus back on these 6 acids. What is the pH of a 10 millimolar solution of perchloric acid? There are 2 equilibria: the dissociation of the acid itself and the autoionization of water. The formal acid concentration is, of course, 0.0100 molar. But there's not any perchloric acid in the solution to speak of, just the perchlorate ion, its conjugate base. The systematic approach to solving this equilibrium has us write down the mass and charge balance equations together with the water equilibrium, which we arrived at a quadratic equation. But when solved for these conditions, the H plus concentration is virtually identical to the formal acid concentration. So a very good approximation for strong acids is that their hydrogen ion concentration equals the formal acid concentration. But we also found that if the formal concentration was very small, then the water came into play, and the quadratic showed how the added acid, being in such a small quantity, had such a small influence on pH as to be negligible. A rule of thumb was that for the solution stronger than micromolar in a strong acid, we could use the approximation of setting the H plus concentration to that of the formal acid concentration, and the error would be less than 1% at even the lowest concentrations. Solving the quadratic produces the right value for H plus. The reason this happens is that water produces its own amount of H plus by its autodissociation. In pure water, it produces a concentration of 10 to the minus 7 molar. The approximation is ignoring that contribution when the added acid is small enough. The contribution can therefore no longer be ignored. The error became even smaller at higher concentrations, as these concentrations, say from 1 molar to 1 micromolar, is the range of common utility. So we generally are always using that approximation, that the pH of the 0.0100 molar solution is the negative log of 0.0100, or 2. One caveat of this is that we have ignored activity coefficients. The coefficient for H plus at this ionic strength is about 0.91, so the true pH is closer to 2.04. But we are not using activity most of the time for our class, just so we don't get bogged down in ionic strength and activity calculations. But note that it does make a small but measurable difference. If, for instance, we added KBr to a concentration of 0.1 molar, The ionic strength of the solution significantly increases. The H plus concentration does not change, but the H plus activity changes so that the pH of the solution is now 2.10. The solution behaves a little less acidy by the addition of the KBr salt. But again, we will mostly put activity behind us. What about strong bases? Well, here's a list of the strong bases that you need to know. The principal list involves the hydroxides of the alkali metals. Note that they do not seem to be as strong as the strong acids are strong, but by strong base we mean completely dissociates in water. They all qualify. The bottom entry is for a class of organic molecule bases, the quaternary ammonium hydroxides. The R stands for almost any alkane chain. For instance, the simplest is tetramethylammonium hydroxide, where R equals CH3. Different alkane chains affect the basicity differently, but they all tend to be strong bases. The hydroxides of the alkaline earth metals, like magnesium hydroxide or calcium hydroxide, can, by some measure, be also classified as strong bases. However, their solubility prevents them from fully dissolving. An example, what is the pH of a 10 millimolar solution of sodium hydroxide? Here are the two equilibria. You can set up the mass and charge balance equations and solve them as before. You can choose to solve for the hydronium ion, and you almost get the expression we had before. Look at the sign for the second term. It's just the opposite of what we had before. You can also choose to solve the equation for hydroxide ion instead, which makes more sense since it is the species in abundance this time. In this equation, the signs are the same as before. As before, we solve the quadratic, but find the hydroxide concentration is the same as the formal base concentration. We make that approximation which solves the problem. The same limit applies as with acids. If it's too dilute, then water's basicity will start to dominate the system. Now, a quick reminder of the interconnection between hydroxide and hydronium ion. We have the equilibrium expression. The equilibrium holds no matter what other reactions may also be involved. If we add hydroxide by adding a strong base, the hydronium ion concentration must decrease to keep this equation constant. So if we find either hydronium or hydroxide, we can find the other by dividing it into Kw. Now we can take the negative base 10 logarithms of the equilibrium expression and get that pKw must always equal pH plus pOH. Since the precise value for Kw at 25 Celsius is 1.007 times 10 to the minus 14, its negative log is 13.997. But since we are dealing with the approximations, it really is okay just to let it be 14. Our approximation is that the hydroxide concentration is 0.0100 molar, the formal base concentration. The pOH is 2. The question is asking for pH, which must equal 14 minus pOH, which equals 12. The problem is readily solved. Again, if the formal base concentration is less than 1 micromolar, you need to solve the quadratic for the correct hydroxide concentration. Watch the sign depending upon whether or not you are solving for OH minus or H plus. And also remember that pH equals plus pOH equals 14 at 25 Celsius. If the temperature varies, that number changes slightly, but measurably.